So, let me tell you a story. It's a tale of two engineers. One of them built this nearly perfect AI model that turned out to be a complete and utter failure. The other one, he started with just a simple notebook and ended up sparking a revolution in an entire industry. It's really a modern-day parable for the age of AI, and believe me, its lesson goes way beyond just code and machinery. So, here's a riddle for you, one that's perfect for our time. How on earth can an AI model that's 97% accurate be a total failure? It sounds impossible, right? Well, that paradox is the very heart of this story, and together we're going to unravel the mystery of how technical perfection can lead to, well, practical uselessness. All right, so our story kicks off with what looks like a perfect model. I'm talking a grand vision, absolutely flawless execution, and incredible accuracy scores. But as you're about to see, the numbers on a screen, they don't always tell the whole truth. Okay, so let's set the scene. Picture a massive power company. We're talking over 7,000 megawatts of capacity. Think roaring boilers, massive spinning turbines, a real industrial giant. And into this giant comes a crystal clear mandate straight from the CEO. Use AI and machine learning to create the smartest power network in the entire nation. The stakes just could not be higher. And this brings us to our two main characters. On one side, you've got the brilliant AI scientist. Straight out of a gold medal university, a bunch of Kaggle competition medals under his belt, a true master of Python and neural networks. To him, the world was the collection of patterns and data. And on the other side, we have the seasoned domain engineer. 15 years on the plant floor. This is a guy who understood the physical reality of the machines. He could literally hear if a turbine was healthy or not. Two brilliant minds for sure, but with completely different ways of seeing the world. So the AI scientist gets right to work and builds this, technical masterpiece. He deployed this whole suite of sophisticated models, using all the cutting-edge stuff, random forest, XGBoost, LSTMs, to predict pretty much everything. From plant efficiency and outages to the tiniest vibrations of a turbine. From a pure data science perspective, it was absolutely beautiful. And wow, the results looked spectacular. The dashboards were lit up with these elegant graphs, and the accuracy scores, they were just astounding. 92%, 94%, then an incredible 97% accuracy for outage forecasting. I mean, on paper, this project was a total home run. The CEO was thrilled. But 3 months later, the CFO was definitely not smiling. Because here's the punchline. Absolutely nothing had changed. Plant efficiency was flat. Outages were still happening. Money was still being lost. The models were mathematically perfect, but the business saw zero impact. A 97% accurate failure. So, what in the world went wrong? And this, right here, brings us to the very core of the problem. You see, the failure wasn't in the code, and it wasn't in the algorithms. It was in the disconnect between the digital patterns on the screen and the physical reality on the plant floor. Look, the crucial point to understand is this. The first engineer was brilliant at finding patterns, a master at optimizing the math, but he didn't understand the physical reality behind the data. It's like he was reading the shadows on the cave wall without having any clue what objects were casting them. And you can see how this plays out in the real world. For instance, the model saw pressure dip and flagged it as an error. In reality, that was just a normal, routine changeover. The model saw big load swings and tried to smooth them out. But guess what? Those swings were actually being instructed by the power grid. The model couldn't know about the real-world messiness of things like fuel quality, or that a vibration spike could be a super serious issue, or it could just be a faulty sensor. Without that context, the data wasn't just useless, it was actively misleading. And now, our second engineer finally enters the story. And he didn't start with gigabytes of data or fancy algorithms. No, he started with something much more fundamental, reality itself. And check this out, he didn't fire up a laptop. He took out a physical notebook. He walked the plant floor. He actually talked to the operators, the folks who had been running these machines for decades. He asked questions. He just listened. He began with reality, not with data. And this question right here just brilliantly illustrates the shift in thinking. The first engineer asked a generic, data-driven question. Can we predict the plant load factor? But the second engineer, he asked a super specific, problem-driven question rooted in a real-world observation that was costing the company money. He wasn't trying to predict some abstract number. He was trying to solve a known, expensive problem. And he didn't stop there. Here's another one. He targeted another specific, costly issue. Auxiliary power consumption was just bleeding money during certain times. By focusing on the why behind these real operational pains, he was making sure that any model he eventually built would be aimed at creating actual value, not just chasing a high accuracy score. So, with these new context-rich questions, the entire approach changed. The goal was no longer to optimize a model. The goal was to use a model to optimize reality itself. And this all builds into a simple winning formula. First, you reframe the problem around a real why. Second, and this is so key, you engineer new features. You literally create new data that reflects physical reality, things like temperature gradients or how much an actuator is moving. And finally, you train a simple model, nothing fancy, on this new, incredibly rich data. So what was the result of all this? A 5% efficiency improvement. Not a 97% accuracy score on some dashboard. A real, measurable 5% gain in the actual, physical power plant. And you have to understand, that 5% improvement wasn't just on a single turbine in a corner of the plant. No, it was across the entire 7,000 megawatt network. The financial and operational impact was just staggering. And this quote from this source just puts it all into perspective. In this industry, a 1% gain is considered a massive win. A 5% gain isn't just an improvement, it's a complete game changer. It's a revolution driven not by more complex algorithms, but by more context. So what's the ultimate lesson from this whole story? Well, it's about the future. And honestly, it applies far beyond power plants. It applies to pretty much anyone working with technology today. This story gives us a name for what that second engineer achieved. It's called decision intelligence. And it's this powerful fusion of AI's amazing pattern recognition ability with the deep contextual understanding that can only come from real-world expertise. The goal isn't just to be accurate, it's to make better decisions in the real world. This final comparison really just sums it up perfectly. Pure AI, that's pattern recognition. It's great at optimizing the math. It sees the shadow. But decision intelligence, that's problem solving. It optimizes reality because it understands the object that's casting the shadow. It's the huge difference between correlation and causation. And this is why this story matters to all of us. The future isn't about AI replacing engineers or doctors or financial analysts. It's about those experts upgrading themselves. The most valuable people are going to be the translators. These T-shaped professionals who are deeply skilled in their domain, whether it's thermodynamics or control theory, but who can also speak the language of data, the language of Python and gradient descent. They are the bridge between the physical and the digital worlds. And so this whole tale brings us to one final crucial question that you should ask yourself. As we all build these ever more powerful AI systems, are we just chasing the vanity metric of accuracy? Or are we focused on the much harder but infinitely more valuable goal of improving reality itself?